Good morning, everyone. Once again, we are back with one and another Star Talk, I should say. The Star Talk is not coined by any individual, but it is a very famous series run by Neil deGrasse Tyson. But we have a Star Talk, very famous popular science lecture we are going to have today. We are having very special, distinguished personality in the field of astrophysics. Before starting that, we are very happy to introduce Regional Science Center Bhopal has completed 31 years in the state of Madhya Pradesh on this 12th of Jan. In communication of science and popularization on behalf of our council, National Council of Science Museums, which is an autonomous non-profit scientific organization functioning under the aegis of Ministry of Culture, Government of India. As you all know, we are here to listen a very renowned scientist, astrophysicist, a figure. I'll introduce him. But before that, we would like to convey that Science Center has always played key role in the state for nurturing scientific curiosity on behalf of our council. On that note, this popular science talk or public talk, whatever you would like to say, is very important in our initiative. Like we have been organizing, inviting scientists from India and abroad, sometimes virtual events, sometimes physical. This is purely physical event. When we do some international talks, so most of the our science centers related network people think we must be organizing global event, European or American or from anywhere scientists virtually inviting. That's a great thing. We are on this planet. The important thing, connectivity. So now I want to introduce, before that, I would like to invite Professor Duncan Lorimer on the stage, along with the Professor Mayures Surnes from IISER Bhopal. And I'll ask my colleague, Swapnil, who can also join on the dais. So now, before introducing Professor Duncan Lorimer, I'll ask my colleague, Swapnil, and he is also very much connected with the Science Center. We are very thankful to Professor Surnis and IISER, Bhopal, especially Director IISER, Professor Govardhan Das, for always supporting Science Center's vision and mission. On that note, on behalf of all of us or our council, our Science Center, I'll ask my colleague and my race to welcome with this proper part, Professor Duncan Lorimer. Professor Lorimer is a renowned figure, internationally celebrated astrophysicist for his co-discovering work like fastest radio burst. Still, we are figuring out from where these are coming, but those singles are very important to understand our universe and may play critical and important role even to understand dark matter and dark energy. We don't have direct correlations as of now, but these unknown sources are very important. And theoretically, people have discussed many ideas and theoretical predictions also, maybe merger of neutron stars, maybe some black hole event like things creating. We don't know exact which are the main source, but we are figuring out. That's the beauty of science. We are always trying to explore, discover, and then analyzing data. Science believes in data analysis. Science believes in a testification theory, then experimentally proving the record. So, sir, Professor Lorimer has contributed a lot in the field. And once again, I'll request you all to give a round of applause for his extraordinary contribution for discovering first radio burst, fastest radio burst, and that is named after him. That whole phenomena is called around the world Lorimer burst. People have discovered after his discovery also. That's a great thing. We have very special lecture today. Professor Lorimer is also well renowned for his teaching and his very important contribution in transient event like pulsars. Pulsar are very important source of lighthouse in the our universe, like a magnetron or like a neutron star is emitting light along the axis, and when it is rotating, signals is keep coming. If it is along the line of sight towards Earth, then the pattern may be repetitive, and that's how we can see this transient event. And his work in this area has pioneered a huge understanding about our universe. On that note, please continue. Okay. You are free to have a round of applause as you like, because this is the most important celebration in the science which we are going to have. And his renowned and internationally celebrated work has earned a lot of international recognition, including SAR prizes. And his book is well known in the field of astrophysics. He's the author of very interesting book, and I think I don't want to reveal the book. If you have a query after the talk, you may discover. That's how we want accidental discoveries also. And science centers are basically aimed for creating critical thinking, hands-on learning experiences. That's how we have today with us. So let me tell you one more time. Please join me in welcoming Professor Duncan Lorimer, ably distinguished scientist from West Virginia University of United States. And we are thankful to ISRO Bhopal and especially Professor Mayuresh Surnis for this collaborative support. Thank you. Sir, the stage is yours.
Thank you very much. Good morning, everyone. You, okay, yeah, I will move around. Thank you. It's such a pleasure to be here. I've been in West Virginia now for almost 20 years, and I tell people there, because I'm originally from the UK, so I tell people there I got there as quick as I can, and it only took me 56, almost 57 years to get to India. This is my first time in India, and I am delighted to be here and seeing all these wonderful cities and getting to speak to all you wonderful people. So I'm going to tell you today about um, this cosmic phenomenon that we found really accidentally 20 years ago, called fast radio bursts. And so you're going to be hearing a lot about them, but here's the first one that we found. And I'll explain this display later on, but just to give you a sense of scale here, this is a few thousandths of a second, a few milliseconds in duration, and it's coming from around about 3 billion light years away, so halfway across the universe. And we just found it by pure luck, pure serendipity, and it's something that we've been trying to figure out ever since, and we're still trying to figure it out. And so maybe some of you will join this discovery and become scientists and try to get to the bottom of this and other mysteries. So here's the phenomenon that we think is happening now over the whole sky. So what you're looking at here is the sky, the whole sky projected onto a screen. Those colorful things in the background, those are is a map of galaxies. Just to give you a sense of the background, the equator here, this is the plane of the Milky Way, and it's hard to see galaxies through the plane of the Milky Way because of all of the dust in our galaxy. But what you see, which is most important for this talk, are these flashes. They're going off all over the sky. So once every few seconds, actually, one of these things is going off. And they're coming from random locations on the sky from great distances across the universe. So, um, let's begin and think about how we observe astronomical objects. We don't just use one telescope. So a few hundred years ago, we were looking at the sky with our eyes, and so we were in the visible part of the electromagnetic spectrum here. But that's only one small part of the spectrum of light. It goes all the way up to the highest energy gamma rays, and the lowest energy, longest wavelength radio waves. And we don't use our eyes anymore. We still do to look at computers and things like that, but we use telescopes over all this spectrum. And you can see some of the telescopes on this slide. Some of them are orbiting above the Earth. That helps them to see the astronomical objects. And some of them are here on the ground. So there's a telescope here, a radio telescope, like the one near me in West Virginia, and one that I just visited here in India. And so that's just part of a whole collection of observatories. There are optical observatories, some of them in space, um, and gamma ray and X-ray observatories, all of these telescopes work together to get a bigger picture of the universe. So, how do radio telescopes work? This slide hopefully explains that a little bit. Let's imagine that you're looking at a galaxy, a distant galaxy, far beyond the Milky Way. And that galaxy is sending light over all different wavelengths. It's sending out gamma rays, it's sending out radio waves, and everything in between. Let's look at the radio telescope here. This is a typical radio telescope. It looks like a TV antenna that often would be on roofs of buildings, and you go outside after this talk, you'll see them all over the place. We use them for TV and just general communications, but they can see distant objects as well. And so the job of this antenna is it's to reflect the radio waves that hit the surface of the dish into the focus here. And that focus, that focuses all of the radio radiation into a single point. It collects all of the energy together, and that energy excites electrons in a wire, basically, in simple terms, inside the telescope. And those electrons in that wire generate a current. And the electrical current that is generated is being produced in effect by the galaxy. So we're using that current to study the radio waves that are coming from the galaxy. And so when we look at the maps that we can make with the radio telescope, they might look like this. You can see the spiral arms. There's a lot of gas that emits radio waves. And then you can compare it to different parts of the electromagnetic spectrum. You might look at this telescope in X-rays, and there you just see the central core of the galaxy. So the point of this slide is to highlight that, again, you can't just use one single telescope to study the sky. You have to use multiple ones. And so what we're going to focus on today is radio waves and optical, mostly radio though. So let's talk a bit more about radio telescopes. So they don't always have to look like those dishes that I showed you. Basically, you just need a wire to collect those radio waves. And the other thing to remember or to realize is that radio astronomy is only about 100 years old. It hasn't been around that long. About 100 years ago, a man by the name of Karl Jansky, shown here, who was an engineer in the Bell Labs in New Jersey in the US. At that time, Bell Labs were trying to discover and really develop the field of communication using radio. And so one of the things that they found when they started sending signals via radio waves was that there was a lot of static. And so Jansky's job was to investigate the source of the static. So he built this thing. It looks like a merry-go-round that you might see at a fair. It's got wheels and a bunch of wires, and it rotates around. It was called Jansky's merry-go-round. It basically, as you rotate it around, it becomes sensitive to different parts of the sky. And so Jansky was searching for the source of the static. And in the course of his investigations, he found out that the radio waves were coming from beyond the Earth. There was a significant source of radio waves that was coming from the sky. Jansky unfortunately died at quite a young age, and he really didn't see what happened to his discovery. And the baton was passed to a person called, picked up really by a person named Grote Reber, who did live a lot longer. Here he is on the right. So Grote Reber was also a radio engineer and physicist, and he built really the first purpose specific telescope to study radio waves. This telescope is about 10 meters in diameter, something like that. It's pretty big. It currently sits in West Virginia, where I'm from, but it was originally built in his mother's backyard in Wheaton, Illinois. And so he used this telescope to carry out the first maps of the radio sky. He showed that the center of the Milky Way had a bright radio source, and he mapped the plane of the Milky Way for the first time. And so this was the first time that we discovered that radio waves could be useful to really understand the universe in a different way. Now, The radio waves are very low energy, right? They're very weak. They don't carry much energy with them. And just to highlight that, if you look at, maybe it's easier to see on this slide, um, you see a lot of zeros here. Um, so our unit of intensity is named after Karl Jansky. One Jansky, abbreviated JY, is equal to 10 to the minus 26 watts per square meter per hertz. It's a tiny amount of power that is falling on the telescope. If you collected all of the radiation that the telescopes have observed over the last 50 years, it would be about as much energy if I release a feather and drop it to the floor. That's about the same amount of energy. It's a tiny amount of energy, and it was very important to quantify that. And so this telescope here it's no longer around, but it was at Greenbank, West Virginia, where I'm from, where in the 1950s astronomers around the world started building observatories, and they wanted to understand the amount of power that we were getting from these telescopes. So they built this telescope with very well understood properties to calibrate that scale. And that's really important because we get a small current with our radio telescope, and we want to actually understand what the source of the radio waves far across the universe is actually doing. So, one other really important telescope in the story, just to talk about here, is known as Murayang. It's the Parkes telescope just outside of Sydney, about 350 kilometers outside of Sydney in Australia. It's a 64-meter diameter dish, and it's in my opinion, one of the most beautiful, one of the seven wonders of the world, but perhaps one of the eight wonders of the world. It's just a beautiful telescope. The observer sits in this tower here, and the telescope. Imagine this gigantic telescope moving above you. It's a very surreal experience. I spent many years um, observing there and many visits to this telescope. And the telescope had an interesting design. It's like a camera. So, it can scan the sky, but like your cameras on your phones, it has multiple pixels. Your phones have like millions of pixels in your camera. The telescope had 13 pixels. So it's kind of like a very primitive camera. But what it means is it can look at 13 different points in the sky at once. And so it can be very productive at scanning the sky. And we'll see how that plays into our story in a few minutes. So that's the Parkes telescope. Now let's think about the radio sky again. So after almost 100 years of doing radio astronomy, what do we know about the sky in broad terms? Well, here is an image of the horizon at Greenbank Observatory, and so there's a bunch of telescopes here. This is close to where I live. But then the sky that you're looking at here, this is not what you see with your eyes. It's what you would see if your eyes were sensitive to 5 centimeter radio waves. And so they're not, your eyes can't see those, but just imagine they were like a telescope, and that's what they could see. This is what the sky would look like. So if you look at this image for a minute, you immediately see all these little points of light. They look like stars, don't they? They just look like the stars that we see with our eyes. In fact, it turns out that they are galaxies that are far beyond the Milky Way, that have powerful black holes at their cores, and those black holes have material that's swirling around them and generating radio waves. And often cases we can see those with our telescopes. So these are all galaxies, these little points of light. And then you look at these expanding objects here, these extended objects, these shells, and you can see that they are not points of light. And it turns out that they are much closer. They're objects in the Milky Way. In particular, this one here is a supernova remnant. So it's the remains of the explosion of a massive star that exploded hundreds of thousands of years ago. And what you're seeing there is the radio emission from the expanding shell of gas after the explosion. At the center of that explosion is something called a pulsar, which we'll talk about in a minute. But this slide is highlighting the difference between radio and optical astronomy and other bands as well. So just bear that in mind as you go away from this talk, that we need all the telescopes to build a full picture. Now, how do the fast radio bursts play into this? So what I'm going to hopefully do is play you an audio file that has two components to it. One, you'll hear a background, and then on top of that background, you'll hear the fast radio burst signals. So let me try to play it, and we'll talk about it in a minute. Okay, so that could go on for hours. I've got a long recording of that. It's basically a simulation. What we've done there is you heard the background noise, that rumble. That's the noise in the electronics. It's basically just the fact that the electronics is at some temperature and the electrons are moving because they're hot. But also, there are sources in the sky that are just contributing to that noise that we can't see. So it's kind of a background nuisance, but it's okay. The interesting stuff was on top of it, and those were like those little chirps that you heard. That's the fast radio burst. And what we did there is we converted the radio waves into an audio signal. So the reason that it went was that you heard the higher. What's so funny? It went because you heard the higher frequency sounds before the lower frequency sounds. That's why it sounded like the way it is. It's called a chirp. That's the technical term. Right? Now, here's what it looks like. So this is a lot what scientists do. They make something really cute, like a noise, into a boring image. But it is important. So let's take a look at this image for a second. What you're looking at here is time. It's about half a second of data. So a very short amount of time. And this is frequency here. So imagine you're tuning your radio dial and you're moving up and down in frequency. And this is the chirp. So this is that's what you heard there. That's the thing. So the highest frequency arrives first and the lowest frequency arrives later. And when you add all of this signal up together, you get this pulse. And this pulse is only about a few milliseconds in duration. So it's less than a duration of a finger click. It's a very short amount of time, but it's there and then it's gone. So why is that chirp? Why do they even have that chirped nature? Because you might expect that all of the signals would leave the source at the same time, and that's a reasonable assumption. But what's happening actually is that the radio signals are traveling across the universe, and the universe isn't completely empty. It's actually got little small amounts of stuff in it. There are free electrons, there's gas, there's dust. There's not much, but there's just enough. In particular, there are just enough electrons to delay the passage of those signals. So the higher frequency signals travel faster because they are, and then the lower frequency signals are refracted more by the gas, and they travel slower, so they get delayed like that. So that's the source of the chirp. It's because they've traveled to get to us. So it's telling us something about their journey as well. And very importantly, it's telling us about how far they've traveled. So the longer the delay, the longer the chirp, um, the more electrons they've encountered, the farther they've traveled. And so this delay actually that we measure here, the delay from here to here, let's say, it's about 300 milliseconds. That's proportional to the distance. And so we call this delay, this measure of the delay, the dispersion measure. The dispersion is this chirp, and so it's a measure of the dispersion. Now, DM, as we heard in the introduction, is often used for dark matter. So don't get it confused with dark matter. This is not dark matter. This is dispersion measure. So when I talk about DM, I'm talking about these chirps. The other thing you heard in the audio is that some of the chirps were louder. and some of them were fainter. And that's just a natural thing that we see in the sky as well. Some of the sources are farther away and they appear fainter, and some of the nearby sources are, are brighter. There is actually a whole range of powers that the sources are emitting, but we don't really see that initially. We just hear them at different volumes. Okay, one more telescope. Um, And this is a very important one because this is kind of where the beginnings of fast radio bursts occurred. So this is going back almost 60 years now to the late 1960s. 1967, astronomers were building this telescope here. It's um, basically a bunch of wires in a field around Cambridge in the UK, and it's really just acting as a giant telescope that is taking advantage of the fact that the Earth is rotating, right? And as the Earth rotates, different parts of the sky come overhead. As those different sources come overhead into the telescope's field of view, they excite electrons in the wires, they generate electrical currents, and we see things. And so Jocelyn Bell, who I think is pictured on the next slide, her job was to look for signals with this telescope. In particular, she was really interested in looking at the twinkling of radio galaxies caused by the material close to the solar system. So she studied that, but more importantly for this talk, she found something else. And so what you can see here is one of her recordings from her instrument. So these are basically sheets of paper, but you imagine there's actually miles and miles of them. She collected so much paper, it would be considered a environmental disaster today. But everything was recorded on paper. This was before digital computers had really taken off and we were able to collect data in the computer. But those miles of paper chart had little signals buried in them that were just popping out above the noise. So this is actually a radio source, but it was really confusing because um, much like optical astronomers have to to combat light in the sky from other sources, radio astronomers have to combat sources of interference. So there are certain things that, like electric fences nearby the observatory, that generate electrical signals that come at random times. So Jocelyn had to be very meticulous and analyze all of these recordings, and eventually she found a bunch of them that were occurring at the same parts of the sky, and they were clearly not coming from the Earth; they were coming from the heavens. And when she zoomed in on this one of these recordings, she saw something like this. So what you now see is a sequence of pulses. So each of these downward dips is a pulse. That's a pulse of radio waves that is about 1 second. Every 1 second, you see a pulse. So it's really important to, when you're scientists, to have pictures of things, of phenomena. And this is the picture that scientists have in their mind's eye when they think about these pulses. And so we now call this phenomenon pulsars. And it stands for pulsating sources of radio. Um, and here in the next slide is kind of a visualization of what's going on. So we have a neutron star, which is produced in one of these supernova explosions that I was just talking about. It's about a 10-kilometer radius star, so it's like about the size of downtown Bhopal, I guess. Sort of no, a little bit too small or too big. Anyway, 10 kilometers. It's something like that. But you have the mass of the sun, and then half the mass of the sun again. 1.5 times the mass of the sun is packed into 10 kilometers. So you almost make a black hole when you compress material that close together. But in this case, what you make is it's called a neutron star. The protons and electrons get squeezed together and basically form a bunch of neutrons in the core, and it's spinning very rapidly. So here's a little picture of the star. Like the Earth, it has a north and south magnetic pole, and it accelerates charged particles from the surface up and down those poles. And as the star spins, you get a pulse. So as the beam passes your line of sight, you get that radio pulse that you see there. And so this, my eyes are really not very good, so I can't see the red dot. This pulse here are these pulses over there. So that's the phenomenon. So you just like a lighthouse, as the beam sweeps past your line of sight, you see a pulse of light. Here, as the magnetic axis of the star sweeps past your line of sight, you see a pulse. So Jocelyn Bell and her supervisor Tony Hewish and colleagues had found a whole new class of radio sources called pulsars. And people like Myresh and myself have spent years studying them. They're fascinating objects to study, and they still are amazing. And we could talk about them for weeks on end, but I only have less than an hour to spend with you today. So I want to cut to the really important part of this story, um, is the connection between pulsars and supernova explosions. You can see it was made in the year 1968, so right after the discovery of pulsars. They found a pulsar coming from the center of the Crab supernova, which was seen by our ancestors in the year 1054 AD. There was a star that was so bright you could see it during the daylight hours. When you point a telescope out to the sky, this is what you see today, this expanding shell of gas. And at the center of the shell is the pulsar, this star that's spinning very rapidly, and it's very compact. It's about the size of Bhopal, approximately, right? So but this star is spinning 33 times a second. It's even faster than the ones that Jocelyn found. It's a very young neutron star, only about 1,000 years old, and the cool thing about this particular star is it emits every few minutes or so. It emits a huge pulse, and these pulses have been superimposed onto this image here. It emits huge pulses that are so bright you could see them well beyond the Milky Way. So astronomers have really been, since the early 1970s, been trying to find examples of this. So this slide just summarizes some of the characters that have been working on this area. And it began with sort of theoretical ideas in the late 1960s about what these sources could be. Nobody really knew, whether they even existed. But because the Crab pulsar was so bright, they figured it was worth looking. And so they're thinking, well, maybe supernova explosions could actually produce these pulses, something like that. And then Vitaly Ginzburg reasoned that you could use the dispersion to actually measure the electrons between galaxies. And that's what it turns out we've been able to do. But back then, people didn't know anything about whether they even existed. So there were a number of astronomers. So John Jelly here was using telescopes in Europe to try to look for radio emission from supernovae. And then in the mid 1970s, Stephen Hawking, very famous physicist who's sadly no longer with us, and Martin Rees, former Astronomer Royal, they came up with this concept of exploding black holes, and those could produce radio pulses. And there was a whole other slew of sources that set a lot of people in motion during the late 1970s and early 80s to look for these pulses. Despite a few false alarms, nothing convincing was found. So people kind of gave up after a while. And in the meantime, people had so much fun studying pulsars that it really, there were plenty of other things to do. But the people that actually kind of helped get us where we are today are shown here. So this is the end of the 1990s, the beginning of the 2000s, 25 plus years ago. So Jim Cordes, Shami Chatterjee, and Maura McLaughlin. So Maura is in fact now my wife. So back then, we just met, and she, unlike me, she looks just as young as she did back then. Oh, but now seriously, she's really deserves a lot of the credit here, because she was the one who developed really a modern way of looking for these pulses. So rather than looking for individual pulses in paper charts, she and the colleagues there shown there kind of developed this idea of computerizing it and making it much more efficient. So here's an output of the search process. So here's another very busy plot. Let me explain a little bit about what's going on here. So you've got time going along here. So this is time in seconds. So it's just over half an hour. And you've got DM going in this direction. So DM, remember, it's not dark matter, it's dispersion measure. The bigger the DM, the greater the distance. So you can think of really this as being distance versus time in a way. So the farther sources are up here, the more nearby ones are here. What you see here is the background noise, these little signals here. That's kind of like the hum that we heard in the recording. And then what you see on top are the individual radio pulses that are coming from this particular source. So there are 3 very bright pulses that are seen. And that's what Mora's code was able to really do very efficiently, is to show us these pulses as a function of DM. So that was really exciting because it allowed us to discover a whole new class of neutron stars that were just emitting these transient radio bursts. Most of the pulsars give steady streams of pulses, but there's this whole class of them that we hadn't seen before that just emit very bright pulses, and we're still trying to figure out what those are. So this is now about 20 years ago. And Maura and I, at that point, we got married and we moved to the UK. And then we moved back to the US. So that's where her family is from. And here we are with our oldest son, who's he's now 20 years old. So he's about this tall. And he's actually studying at our university. So we've been at West Virginia University for just almost 20 years. And as any professor will tell you, one of the purposes of universities is not just to teach, but it's also to get the students to learn by doing research. And so we had undergraduate students wanting to do research with us. Here's one, Ash. And Ash's project was to look for pulses from these things here. Does anybody know what these 2 cloudy objects might be? No, no, no. Anyone? Anyone? They're not quite visible from here. You have to go a little farther south. They're called the Magellanic Clouds. Has anyone heard of the Magellanic Clouds? No? They are our nearest neighbor galaxies. So they literally look, if you get the opportunity to go below the equator on the Earth, you will see these if you look long enough. And they literally look like clouds in the night sky. But they're actually, this is a comet, of course, don't pay any attention to that. But there's 2 of these cloudy objects here, and these are nearby galaxies. So they're about 180,000, 200,000 light years away, something like that. Yeah, so we were looking for pulses in these galaxies. So the idea was search for things like this, which are in the Milky Way, and to go over here and look for them way out in these distant galaxies. So that was the project, and this is how we ended up finding these other pulses. But this was a great project because it allowed us to just it was just at the time when computers were fast enough that they could process the data, and you could, a student could have just enough work to do such that they could look at some of the output and kind of classify things. And so I would meet with Ash once a week, and we'd look at plots like this. So again, this is time and dispersion measure, so basically distance going this way. In this case, you've got almost 2 hours of data. It's a very long observation. And you see, about a dozen different pulses here. And this turns out to just be a known pulsar that occasionally emits brightish pulses in the Magellanic Clouds. So we didn't spend too much time on that. It just tells us that everything is working. What we got really excited about one day was when Ash found this. And so it's a huge pulse, very, very bright. It's this thing that you see in the back of the slide. And this is how it first looked to us when we analyzed the data. So it came in about half an hour after the observation started. It has a rather large DM. And here's our 13 pixel camera that I told you about earlier. So that's the footprint that the telescope sees on the sky. What you're looking at here is a map of the sky. In particular, this is the Small Magellanic Cloud, the smaller of those two galaxies. And it turned out that we had observations that covered the whole region here, but what we ended up looking at was an extra bit of data that was looking a couple of degrees south. And so basically, we were looking somewhere out here where the dot is, like 2 degrees away from the galaxy. So we weren't looking at the galaxy at all. We were basically just looking out into the universe, and we found this ginormous pulse. By ginormous, I mean very, very bright, really so bright that it just seemed too good to be true. And we didn't really know what to make of it at first. But as we started to piece things together, this is the picture, probably the most important slide on my talk here, that this is the picture of the phenomenon that we now think is fairly accurate. So here's our home, the Milky Way. This is all artistic license, of course. We can't get outside our Milky Way and take a picture, but this is what we think it would look like. We live somewhere in the outer spiral arms here. And this is the fast radio burst. We didn't call them fast radio bursts back then, but this is what they're now known as. And we don't yet know what it's coming from, but we think it's being produced in other galaxies, as you'll see. Anyway, so the burst travels all the way across this part of the universe to get to us. On the way, it might hit some gas from intervening galaxies. It might even go through intervening galaxies. And so what happens is all that dispersion that we learned about earlier that accumulates. And so the pulse that we see today, which is this one here on the right, that's what we observed, just like a little thumbnail. That is basically like a record of the pulse's journey through the universe. So just like when I came here to India, I got my passport stamped as I entered the country. This is kind of what's happened to the pulse as it's traveled across the universe. It's kind of got its imprint stamped as it left the source. All of the frequencies left at the same time. As it leaves the host galaxy, it has a little bit of dispersion, but most of the dispersion it gets is around the next 3 billion years. And eventually it enters the halo of the Milky Way somewhere around here. And then 30,000 years or so later, it lands on the telescope. And so all of that dispersion basically adds up. And so it provides us a lot of clues that we'll use as we see later on. So that's the dispersion. But I did tell you it was incredibly bright. So we made a guess at its distance based on its dispersion and some of our knowledge about how many electrons there are in the universe at the time. We came up with a distance of 3 billion light years. So it was an educated guess, but it was by no means a measurement. But it was good enough to tell us that the burst that we found, and as mentioned in the introduction, it was ended up being named after me. There it is. What you're looking at here is luminosity, so the total power that's being put out. So your light bulbs have a luminosity. That's, when you put a light bulb in, you look at the luminosity. That's basically just a measure of the power. And what you're looking at along here is the pulse width. So these are all pulses from pulsars, and so they're relatively low power. There's some giant pulses over here, but the burst is sticking up here. It's actually 10 to the 12 times, so 1,000 billion times, 1 trillion times brighter than the brightest pulsar pulses. So that was really exciting. It turns out it puts out the same amount of power of energy, releases the same amount of energy that the sun does in a month. This source puts out in 5 milliseconds. So they're pretty bright by astronomical standards, and it seemed to be something entirely new. So what was it? And we still don't know the answer to this, but we have a lot of clues. And one of them is that the burst was very short in duration. It only lasted a few milliseconds. And so you're probably aware that galaxies are like hundreds of thousands of light years across. So they can't organize themselves to all produce light at the same time. It has to be something that's much smaller that can organize itself to radiate in such a way that it can produce a pulse in 5 milliseconds. So that means it has to be something like a few hundred kilometers or less in size. It has to be quite a small object. something like a neutron star, perhaps. Um, and it puts out a lot of energy, and maybe it's just going off only once. So objects that might fit the bill here are inspiraling stars. So here's an animation or a picture of two stars that are inspiraling. And when they inspiral, when they hit each other, they could produce a pulse. Here's an exploding star that, as we heard earlier, is theorized to produce a radio pulse. We haven't yet seen direct evidence for that, but it might happen. And then over here, here's an artist's impression of a really high-powered neutron star known as a magnetar, a really highly magnetized neutron star that, like the sun, undergoes solar flares and can also put out radio pulses. So things like that were our best guesses at the time. And we didn't, pretend to know all the answers, but we'd made a start. So now it's 20 years later, and it's interesting, just as a side note, to note that the fast radio bursts have kind of started seeping into popular culture. There's a book that I am not promoting here, but it's a relationship book that the fast radio burst appears in. It's a if this burst can travel across the universe, then you can sort out your relationships at home, type of thing. So there's that. And then there's a German instrumental rock band who have the name Lorimer Burst. And so so you might want to check them out afterwards. They make quite nice music. I've actually met them online. They're interesting characters. And here's one of their albums. It's called Dispersion. So you can check those out. So it's just interesting how these scientific memes, I guess, kind of enter the popular culture. All right, back to the story. So in 2007, so almost 20 years ago, we put out our findings. And I'm not going to read all of this to you, but this is like the summary of the paper. And one of the findings that we made, or one of the predictions that we made, is that hundreds of these events could occur each day because we'd only looked at a small part of the sky for a small amount of time, and we figured that they were going off all over the sky. And if we could detect them, we could use this dispersion to serve as probes of the cosmos, specifically probes of the material in the cosmos. Turns out that's what's happening. But to get to where we are now, we had to have there was a few obstacles along the way. And one of them happened fairly early on. So around about right after the discovery in 2007, people started to find more and more, or they wanted to look for more and more of these sources, but they weren't initially very successful. There were lots of data sets out there that people wanted to find more and more of these bursts in, but instead of finding further examples, they found things like this. And it kind of has, it has some interesting structure to it. It doesn't, but it has a delay. But what I'm not showing here on the image is it actually shows up in all 13 pixels of the telescope's camera. And so that's not something that's hitting the surface of the telescope. It's something that's getting in from the ground, or close to the ground, perhaps, that's going into the camera, and it's a source of interference. And so these sources were dubbed peritons. Here's a periton. This is a mythical Greek elk that casts a human shadow. You can look it up on Wikipedia if you don't believe me. There's a picture of it. So it's basically a pulse that is masquerading as an astrophysical signal. And Sarah Burks-Belair, one of our colleagues at West Virginia, went back then. She was a student in Australia, and she was the first one to catalog these. And so they kind of confused the story because instead of finding more fast radio bursts, or Lorimer bursts, we were calling them at the time, we just kept finding these peritons, and they clearly weren't helping. So it took quite a long time for really the technology and for us to look at enough sky and collect high quality data to really make a breakthrough. That was fortunately done by Dan Thornton, a PhD student at Manchester, and a host of collaborators here in 2013. And they found 4 more of these bursts. And you can see them here. These are the 4 different pulses that they found. that's when they named them fast radio bursts. That's a much better name. That's more descriptive. So fast means short duration, and then radio burst is fairly descriptive in itself. Here's our original one, and here's another one that was found at the same time. What you're looking at here is a graph of dispersion measure, basically versus the angle from the galactic plane, the galactic latitude. These red dots, red crosses, are the pulsars in the Milky Way. That's the gas in the Milky Way that's producing these. And you can see how different these guys are. They're not following the distribution that you expect from the Milky Way. So 2013 is really when the field started to take off, but we still had this rather strange conundrum about what is producing the peritons. So that wasn't really sorted out until about 2015. So the peritons turn out to be coming from microwave ovens. So you've all used a microwave oven, I'm sure, and perhaps you've been in a hurry. You've put your snack in there. You're sitting there waiting for it. Checking your phone or whatever, and you say, "Oh, I just need to have my snack," and I pull the door open. But when you pull the door open, you actually release a radio pulse if the microwave is still running, because the electrons that are spiraling around inside a little device called a magnetron to generate those microwaves. And when you pull the door, the electrons slow down and they generate this dispersed pulse, and it leaves the microwave oven door. So here's John, one of the scientists at Parkes, who's for some reason using a pool cue to open the door. And Emily Petrov, one of the students at the time in Australia, had basically just commissioned a new real-time observing system. So prior to 2015, it took us a long time to process the data to find these fast radio bursts. But now in 2015, or since 2015, computers have been fast enough that we can see them in real time. So the computers can just process the data and show us the pulse. So Emily was in the Parkes control room on the other end of the phone, and John was saying, "Okay, I'm opening the microwave oven door," and then Emily would see the pulse on her screen. So it was real cause and effect for these peritons. And an interesting plot that they made around the time was the number of bursts that the telescope was seeing versus time. And the peritons are color coded in pink here, if you can see them, and they're all occurring at around about lunchtime, Parkes time. So this is the time when the microwave was most in use. There's a canteen at the observatory, and so people were opening the microwave doors most in lunchtime. The fast radio bursts are color coded slightly differently. At that time, there was about a dozen known, and you can see that the fast radio bursts have no knowledge of lunchtime. They're all across the chart here. They've come across the universe. They don't care about lunchtime. And so our initial discovery was made here. It's one of these points. So that put to rest that story. So the rest of the talk, I will just try to bring you up to speed about what we know about fast radio bursts. And in 2016, a big breakthrough was made in that for the first time, people saw a fast radio burst that repeats, these so-called repeaters or repeating fast radio bursts. Up until that point, we'd looked at the fast radio bursts multiple times, but we'd never seen any follow-up bursts. And so we were starting to think that maybe they only appear once. And that may still be true for some of them, but at this time, this was the first one where we could see the repeat bursts really clearly. So here's a bunch of bursts from that source. And Laura Spittler and Paul Schultz were the key players in this. And crucially, it ruled out explosive origins for the source, because this would only happen once. And also things like this, where the two stars would merge, this would only happen once. But maybe things like this, where the source was periodically generating large pulses, is still possible. So it was something episodic that is producing these repeating fast radio bursts. So that was a big breakthrough. The other thing that happened is that in 2017, the first burst was localized, And it was done by a couple of students originally from India. So Shami Chatterjee was at Cornell at the time, and Sriharsh Tendulkar eventually ended up back at TIFR in Mumbai. He's gone back into industry now, but at the time, what these guys did was they used the the Very Large Array in New Mexico to synthesize a giant telescope with a really exquisite resolution on the sky, so you could really pinpoint where these bursts were. Because up until that point, we just used telescopes that didn't have a great resolution on the sky. They couldn't tell you exactly where it was, apart from it's kind of like the size of the full moon. It's somewhere in that part of the sky. But now with the Very Large Array, the fact that we knew this source was going to repeat, Shami was able to localize it to this little pinpoint here. And when Sriharsh made an optical image of it, they realized that it was actually coming from this galaxy, uh, which is a dwarf galaxy at a distance of a few billion light years away. So this was the first time that it was definitively associated with a galaxy. And because astronomers know how to measure the distance to galaxies, they could measure the distance to the fast radio burst. So that was a really big deal. And then since then, it's been a matter of building up the numbers. So science is all about collecting data and trying to understand, trying to look for patterns, understanding your samples and your observations. And so since then, we've been collecting a large catalog of fast radio bursts. We currently know of over 4,000 of them, individual bursts, around about 3,600 individual sources, something like that. And a lot of that progress is due to this telescope here. It's called CHIME. So CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment. So it's another strange radio telescope design. It's 4 cylinders here that basically track the sky as sources move past the meridian. And CHIME is so sensitive and it has such a wide field of view on the sky. It's about 200 square degrees. To give you some perspective, the full moon is about half a square degree or a little bit more than that. So it's several hundred times the size of the full moon that it can see on the sky at any given time. And so that allows us to detect a few FRBs every day. So that may not sound like very much to you, but over time that adds up to a lot of sources, and there's a lot of things that the scientists can do with that. And so, in particular, they started finding FRBs and localizing them to distant galaxies. Another thing that they were able to do was to classify the bursts into basically repeating sources and one-off sources. So because the telescope is looking at the sky day after day, same sky it sees, now for 6 years, it's able to monitor the sources that repeat and then just see the ones that don't repeat. And so when you do that, you find that there's some interesting differences. The one-off sources, the sources that we see once, they tend to be broadband. We see them over all of the radio frequencies, whereas the ones that repeat have this rather complicated frequency structure. And since you guys like the chirp so much, I'll just make a slight anecdote here. People in the field call this type of feature where you get this sort of descending sequence of notes. It's a sad trombone effect. You're all familiar with the cartoon when something bad happens and it's like a so that's basically what that is. That's a sad trombone, but it's a much more complex structure than the one-off sources. So the repeating sources seem to have different phenomenology, is what we say. All right, another big breakthrough happened in what was for many of us an awful year, 2020. During that year, astronomers found a very bright signal in the Milky Way. It was coming from one of these magnetars, these highly magnetized neutron stars that is emitting basically flaring events. And this particular magnetar had been known for many years, and so we were immediately able to associate the pulse from it. with the astronomical source. And so this is the first and currently the only time that we see a radio pulse with a pulse at different energy bands. And so in this case, it was X-rays. So this is really important because it really strongly suggests that some fraction, maybe a significant fraction of fast radio bursts are coming from these magnetars. We're getting towards the end of our discussion here. So you might be wondering, well, what is the most distant source you found to date? And this has come relatively recently. So you're probably familiar with the James Webb Space Telescope. And a fast radio burst that was seen with a telescope in South Africa was pinpointed well enough that it could be localized with a galaxy that they could see with the James Webb Space Telescope. So here's the basic picture of what happens. So imagine that the host galaxy is over here. It emits a pulse. We're just over here. Maybe this is before humans even existed. This is billions of years ago. Or maybe the Earth didn't even exist when the pulse left. But anyway, time marches on, but the universe is not static. You probably know that the universe is expanding. It's getting bigger and bigger. And with that expansion, the wavelength of the source gets longer and longer, such that by the time it does reach the Earth, it's been stretched. And the stretching, compared to the wavelength that it was initially emitted at, that stretching tells you about the size of the universe through this little formula here. So the observed to the emitted wavelength is basically equal to the size of the universe today compared to the size of the universe when it was emitted. And that's we encapsulate that by this number, this thing that we call the redshift Z. So a redshift of 0, 1 plus 0 equals 1. That means the observed and emitted light have the same wavelength, and that's a source that's very nearby. But in this case, the redshift was 2.1, so 1 plus redshift is 3.1. So that means that the universe, was about a third of its current size when the source was emitted. And in terms of like a look back time in the universe, that's about 10.7 billion light years, something like that. So here is the spectrum of the light that was used to get these observed wavelengths. And because the universe has expanded so much and the galaxy is so far away, it needed the James Webb Telescope to be able to. It needed the wave band that the James Webb Telescope could see. The Hubble could not do this experiment nearly as well. So that's the most distant one. And one of the final things that I'll mention now is that really FRBs, we see them everywhere. To date, we have over 3,000 sources. And so far, we've found over 100 of these connected with distant galaxies. So there's 100 galaxies whose redshifts we've measured. And here's a little gallery of some of them. And they come up in all sorts of shapes and sizes. So we have interacting galaxies, we have spiral galaxies, we have sort of more like elliptical galaxies, irregular galaxies. So FRBs are everywhere. And what they're now being used to do is basically probe the electrons along the line of sight to the universe. So if you think about that slide that I showed you earlier on, they're now starting to measure those electrons directly. What we've got here is basically a plot of dispersion measure versus redshift, and these are the fast radio bursts. So what's interesting here is that the amount of scatter in this plot is telling us something about how the gas is distributed in the intergalactic medium versus the gas in the halos between galaxies. And so that's what astronomers are doing. They still don't know what the source of the fast radio bursts is, but in this case, it doesn't matter. We're just using them as like probes of the universe. It's kind of like when you have a dipstick and you measure the oil in your car. You just stick this probe into the car, and it tells you how much oil there is. You're using the fast radio bursts in a very similar way. You can think of them as dipsticks of the universe. I don't know if that will ever catch on, but that's kind of what they're being used for. Okay, so there's a lot of open questions, and I'm not going to talk about all of them on this slide, but there are many surprises that we can expect in the next 5 to 10 years, and perhaps some of you will be part of that. One of the interesting things that's happening is that a lot of telescopes are coming up, not only in the radio, but also in the optical and gamma ray, but also in a part of the spectrum that is different from electromagnetic light, a sort of a complementary spectrum, if you will, called gravitational waves. So the gravitational wave spectrum is coming from the accelerations of massive objects, and those are being used. Those carry information in many different waves, different ways. So my colleague here, Mayuresh Cernis, and colleagues in India are using a telescope in India to measure the low frequency gravitational wave spectrum. What might also happen with fast radio bursts is that we have in spirals of neutron stars that generate high frequency gravitational waves. And we might actually see a coincidence between a fast radio burst and a neutron star in spiral. So that's very exciting. And it all pertains to the fact that the future of astronomy, and here in particular radio astronomy, is very, very bright. So we're building lots of new instruments. Computing is getting faster and faster, and there is a lot more that we can do. We're only really just getting started. We expect with some of these new instruments to find about 10,000 fast radio bursts per year. In a single year, we're expecting a doubling of what we already have. So that's insane. You'll start to get more of these fast radio bursts than we'll ever know what to do with, but we'll be able to study them in so much detail that I'm sure we'll find a lot of interesting surprises. So none of this work would be possible without support of many organizations. This is true for science in general. So my science is supported by the organizations listed here. They range from state agencies to federal agencies to foreign collaborators. We have many collaborators around the world that we're very fortunate to work with. Science is not done in a vacuum. That's certainly true for every branch of science. So, I know that many of you don't pay taxes yet here. You're too young to do that. But thank you your parents for paying taxes and supporting science here in India and around the world. I'll end there and thank you very much for your attention.
Thank you, Professor Lorimer, for such a wonderful talk. And it's very quite inspiring. I think most of us, the young minds here in the audience, even on live streaming, they might be interested to know that this work is well much supported and collaborated by Indian research students also globally. So we have a very large hope. And he mentioned that one of you one day may be contributing on those fundamental questions which are still unanswered. Or maybe we are probing our universe back in time. So on that note, we'll open this forum for Q&A session. We will take a few questions subject to time frame, but let me tell you one thing, interacting on such matters, not interacting with the universe, interacting with the human quest, we need to have more deeper understanding about our own universe. This may be one of the universe. There are many. Theoretically, we are predicting multiverse theories. So he is looking fast radioverse in our own observable universe. So before opening forum, and I think setting this stage, may I ask one question on behalf of our team or audience? Are these FRBs may serve a critical role in probing universe back into time the way we are using JWST, one of the advanced space telescope ever launched by humanity in the orbit like L2 point, so around 1.5 million kilometer far side of the Earth, not towards the sun, that observing universe in infrared. So redshift is very critical part, as you have mentioned that, so that can enhance our understanding. What is your take on that as a probing our universe back in time? And that is kind of, time traveler.
Right. The universe is a time machine. As we look out into the universe, we look at what it looked like further and further back in time. So we can see fast radio bursts, as I mentioned, over 10 billion years into the past. But that universe, so the universe that we, as in our current understanding, is about 14 billion years old. So we can go almost to the beginning, but we're quite excited now to take that even further and go to redshifts of 3, 5, and perhaps even 10. At that point, we start getting into a phase of the universe where the first stars were just ending their lives and the first galaxies were forming. We think there are neutron stars present in that phase, and so we can use any fast radio burst that we see to probe the density of the universe, the electrons in that part of the universe at that time, in a way that's unique to any other and complementary to other methods. But we'll need telescopes like the JWST to help us do that. The JWST recently found a galaxy at redshift 14, so that has hope for us that we might find a fast radio burst associated with one of those galaxies. So it's a very exciting time, and yes, I think there's a lot that fast radio bursts will have to say.
Sir, I wanna know that how FRB from magnet star and FRB from pulsars are different because magnet star is a highly magnetized neutron star and pulsar is the rotating neutron star. So how it is different? I'm so curious to know about this.
Yeah, that's a great question. So the biggest difference between magnetars and pulsars is magnetars are their energy source is dominated by their magnetic field, whereas for pulsars, the rotational kinetic energy of the neutron star is what powers it. We're not yet convinced that pulsars can, by themselves, can really generate fast radio bursts in significant numbers. There might be episodes where the things fall onto the neutron star, like comets and planets fall onto the neutron star. Those could generate fast radio bursts. The neutron star itself could collapse to a black hole and generate a fast radio burst. But it seems like the magnetars have more promise because their magnetic field lasts for a long time, and it can produce outbursts over many decades and millennia. So the types of repetitive behavior we see are most consistent with magnetars at this time. What I don't want you to all leave the talk today is thinking that all FRBs are definitely coming from magnetars. We don't know that yet. What what it looks like to me, um, if I go back maybe to this slide, when we look at them in all these different types of galaxies, some young galaxies, some old galaxies, even in globular clusters where star formation is no longer going on, we see fast radio bursts. What I didn't mention in this talk as well is that some of the repeating FRBs, just a few of them, have episodic motion that could be linked to a binary system. But that's not true in general, at least as far as we can tell. So magnetars are a strong contender, but they're probably not the only source. Let me say this: it's easier to generate that type of energy with a magnetar than with a neutron star.
Thank you, sir. My name is Adarsh Pandey and I am from Excellence College. The question is, given the extreme density and gravitational pull of neutron star, why isn't these electromagnetic wave or light get not be trapped around the neutron star, similar like to the black holes?
Right. So it's just not because the escape speed around a neutron star is less than the speed of light. That's the quick answer. So you have these in a neutron star. You have probably a fairly simple magnetic field structure that's anchored to the surface of the neutron star. Even as you're co-rotating with that neutron star, you can get up to fractions of the speed of light, but you're still below the speed of light. So light will propagate freely out, and it's directed, and it's actually generated by the magnetic field. So there's an electric potential that is generated across the magnetosphere of the neutron star that accelerates those electrons out. And so that overwhelms any gravitational influence.
Very good afternoon. Sorry about that. Very good afternoon, sir. My name is Ram Tiwari. I have been a student of filmmaking, so apologies in advance if my question is a little off. I'm not from science background.
Okay.
So my question is, a pulse is a burst of energy, a short, brief burst of energy, as much as I understood. The Lorimer burst you very famously discovered, sir, was very short and brief. My question is, did we ever hear back from that friend of ours? And what about that new class of object that you said? It is like a new class of object.
Right.
What do we know with the help of your discovery? What do we know about that particular object? It probably was not a star.
Right. Yeah.
So how your discovery helped in knowing that that class of object? And my question is that.
Yeah, so I think you're getting at like the original burst, the Lorimer burst. Have we ever seen it burst again? The quick answer there is we haven't. Initially we looked for 90 hours with the telescope, and we didn't see any repeat bursts. Then over the years we've collected, hundreds of hours of time just staring at that sky. It starts to get a bit boring after a while because you're sitting there and not seeing anything. It's important work, but it's hard to justify. So far, we've not seen any repeat bursts from that. The other problem with that initial source is we weren't able to really pinpoint it on the sky well enough. We had multiple detections in the receiver system, but we couldn't really localize it to a galaxy or an astronomical object. So we still know relatively little about that source. And so what it really helped us, though, to do is to say, okay, these things exist. We now have to develop the technology to go and find them, more efficiently and then pinpoint them on the sky straight away, because we'll never be able to really do that again for that initial source unless it starts repeating.
Yeah, so probably it wasn't stable at that point because, as you said, pulsar, it repeats that pulse because whenever the pulse passes through our horizon, it repeats that pulse. So was that object was not stable in the sky? Is that what we can assume?
We don't really know is the short answer, but it could just be a one-off event like an explosion that was highly unstable, but it could be just a source that repeats on a very long time scale, longer than human life cycles. Yeah.
Thanks a lot.
Good afternoon, sir.
Good afternoon.
So my name is Aarti and I am a MSc first year physics student from Manit, Bhopal.
Okay.
Manit. My question is how the fast radio burst will help us to find more information about the dark matter, and is really connected to the dark matter, and what type of more different maybe is it really give us some information, and what type of information is giving us?
Yeah. So the fast radio bursts, they're not directly probing the dark matter, so they're probing the baryons, the electrons, specifically the electrons in the universe. Those are what it's probing. But as we build up more and more of these samples, as I said at the end, we're going to get tens of thousands of points on this graph. You'll actually be able to use the fast radio bursts to measure the Hubble constant and other cosmological parameters in an independent way to current techniques. So in doing so, because the Hubble constant and the other cosmological parameters, are pinned to our understanding of dark energy, then, in that sense, they will help with that story. But that's a few years ahead. But yeah, there's definitely some promise there.
Hello, sir. I am Rachna from St. Mary's School. I am a physics teacher. Sir, I want to ask you one very simple question. As you have told, FRBs exist for a few milliseconds and it's very energetic. Yes, sir.
Yes.
And sun is also a huge source of energy. So I want to know, is the energy released from the sun is greater than the FRBs, or FRBs releases more energy than the sun?
Yeah. So the FRBs in a given second, they release more energy than the sun does. So that first burst that we found, if you collect all the energy from the sun in a whole month, the time it takes for a sun to rotate, in fact, you collect all of that energy, that's the amount of energy that we're seeing in a fast radio burst. So they're brighter than stars, but they are actually less energetic than, let's say, supernova explosions or gamma ray bursts, because we're dealing with radio energy, radio wavelengths. So it's low energy emission. So hopefully that clarifies things a bit.
Thank you, everyone, for such a wonderful interaction. And I'm glad that you all are interacting and you have lot many questions. So after this, stopping this live streaming and this talk on the dais, you feel free to interact if you want. For a few minutes, we have Professor Duncan Lorimer here. On that note, on behalf of such a wonderful, curious audience here in the auditorium, let us give a round of applause for such an inspiring talk by Professor Duncan Lorimer. He is a fellow of Royal Society, the renowned, prestigious society. He is also fellow of Royal Astronomical Society and American Society, and lot many things. But he's a great human being, an inspiring figure in science. On that note, on behalf of our council, National Council of Science Museums, Regional Science Center Bhopal, we once again thank you so much, sir, for giving your precious time and coming all the way to the Science Center and inspiring these upcoming young minds. Thank you so much.
Thank you so very much, sir. Now, as a token of remembrance of this particular event, may I please request our project coordinator Sake sir to bestow this memento to our Duncan Lorimer sir, as a token of remembrance for this particular event. Ram. So this is from Regional Science Center Bhopal and from all of you as well. So can we have a thundering round of applause for Professor Lorimer? Thank you. Thank you so much, sir. So for now, the program is closed. If you have any question, you may please interact later with sir. Thank you so very much.